Welcome to AMR-RMA Lecture. I'm Sergey Tabachnikov, and I'm hosting this meeting. It's my pleasure to introduce the speaker. It's Anton Zorich, who is a great mathematician, also an old friend. I'm trying to figure out for how long we know each other, and I'm not sure exactly, but it's certainly a two-digit number, and the first digit is 4. That's for sure. Anton, you can correct me if I'm wrong. So Anton is a distinguished professor at Institute of Mathematics Jussieu. It's Paris 7. He has PhD from Moscow State University in 1987. His advisor was Sergei Novikov. He was an invited speaker at the International Congress of Mathematicians in 2006 in Madrid. He has something named after him in mathematics, which is, I think, the highest distinction. It's Kontsevich-Zorich cycle. Maybe there is something else, but at least this one. And his work is an impressive combination of theoretical and experimental results. So he is one of the prime practitioners of experimental mathematics. And let me finish my introduction by quoting what Vladimir Arnold quipped once, that mathematics is a part of physics. It's a part where experiments are cheap. So without further ado, Anton Zorich, random square tile surfaces and random multicurves in large genus. One last thing, if you want to ask a question, please ask by chat, and we will read them. Thank you. Anton, please start.
Thanks for the introduction. Thanks for the invitation. It's my pleasure and my honor. Before I turn the slide, I would like to say that all what I'm going to tell is based on joint works in collaboration with Vincent Delacroix, Elise Goujard, and Peter Zograff. And I feel myself like ambassador of certain domain of mathematics, and I will try to tell some fairy tales from this domain. And initially, they might seem unrelated and eclectic, and I hope that at the end of the talk, I will glue things together. And I would like to start with counting of square tile surfaces. And as we'll see later, secretly, we would be computing Maser-Rich volume of the moduli space of quadratic differentials. But first, square tile surfaces. So this is a very concrete object. It's not, it's here. So you have a simplified Lego game. You are given plenty of identical squares, or here rectangles. In the sense, rectangles are even better because my squares would be polarized. I would know for each square which two opposite sides are vertical and which are horizontal, and I'm gluing horizontal sides to horizontal and vertical to vertical. And this is a more formal definition. But basically, the true definition was on the previous slide. The only comment concerning the square tile surfaces is like this. You can assume that your unit square is chopped out the complex plane. Just you take the standard square 0, 1 times 0i, and then our square gets endowed with a complex structure, and the surface which we construct also gets endowed with a complex structure. And moreover, if we consider their quadratic differential dz squared defined on each square, you glue from this dz squares a globally defined quadratic differential on the corresponding Riemann surface. So basically, we get a Riemann surface endowed with a meromorphic quadratic differential. But we would not use it really. We would basically only work with these things combinatorially. And now the setting of the problem. So we fix so I assume that we're constructing only connected surfaces, only oriented ones, without boundary. And the parameters which we impose are the genus of the surface and the number of corners with cone angle pi. That's the points where the only two adjacent squares will see one. We will see points like this shortly in one of the next slides. So I fix these two parameters, and then I take huge number n capital of squares, and I'm trying to construct all possible square tile surfaces of genus G with n corners of angle pi, using at most n capital squares. And I would like to find asymptotics for their number of such square tile surfaces. So now I will have to show a scary slide. Don't be, so it's, I think it's the most scary slide of the presentation. And finally, it's not that scary. So it is known that one can consider Riemann surfaces in families when you fix the genus G and the number of mark points. You get a finite dimensional family, which is called moduli space of surfaces. And it admits very nice Deligne-Mumford compactification. And now I need to consider very natural vector bundles defined over this moduli space. Namely, since each point of our moduli space is a Riemann surface with n mark points, and I assume that I always know which point is the first one, which is the third one, which is the nth one. So I can choose for example, the third point, and I can consider a tangent plane to this point to the surface. In complex geometry, they prefer to say that we have a complex curve and that we have a tangent line, or even better, by some reasons, it is convenient to consider cotangent lines. We have, so when we start to deform the complex structure and deform the location of our point, so we get a family of lines, and for every point of the base, for every point of MGN of this moduli space, we get a line. So it is not surprising that this family of complex lines forms a vector bundle over MGN. Actually, one can check that this vector bundle is a holomorphic vector bundle, holomorphic line bundle, because we're bundling lines. And moreover, this bundle can be nicely extended to this compactification, MGN bar. So when you have a vector bundle, you can associate its Chern class to this vector bundle. So when we have a line bundle, holomorphic line bundle, there is only one Chern class, the first Chern class of this thing, and it is denoted by psi I. It's the first Chern class of this tautological bundle, which corresponds to point number I. If you prefer, you can consider this as a two-form. And when we have two forms, we can take wedge products of them. So we have n two forms, one for each line bundle. And as soon as we have a partition of dimension of the moduli space, which is 3G minus 3 plus n, so this is the complex dimension of the moduli space, we can consider any partition of this number into sum of non-negative integers. And then every sum of non-negative integers like this defines the following form of top degree. So we take form psi1 power d1, wedge psi2 power d2, etc. So the degrees are chosen in such way that this form becomes the volume form. We can integrate it over the base, and we get a number. So we get a whole bag of numbers which are parameterized by partitions of the number 3G minus 3 plus n by these non-negative integers. So, and if you prefer, of course, you can consider just cohomology classes and consider multiplication and cohomology and consider corresponding class and integrate. You get numbers. So notation on the right, this is notation from geometry, and notation of the right has name intersection number. Notation on the left, basically you can consider it's just a formal notation which encodes this partition D1, etc., Dn. And this is notation from physics. Physicists call these numbers correlators. If this compactification, so if MGN bar would be a nice complex manifold, these numbers would be integers. But this thing is an orbifold, so these numbers are rational, positive rational numbers. And somehow they appear in various domains of mathematics surprisingly often and sometimes completely unexpectedly. So they're kind of stars of last decades of modern mathematics, and in particular, the famous Witten's conjecture claims that these numbers satisfy certain recurrence relations. So one of the ways to encode this recurrence relation is to construct a generating function which englobes all these numbers for all genera and for all n. And then Witten's conjecture claimed that this generating function, so-called partition function in two-dimensional quantum gravity, satisfies some differential equation. Another way to formulate this conjecture is purely combinatorial, which is just recurrence relations directly for these numbers. We'll see it at the end of the lecture. So it's equivalent. Witten's conjecture was proved by Kontsevich, and then there was independent proof by Okounkov-Pandaripande and by Maria Mirzakhani, by Kazaryan and Zvonkin, and they are more conceptually different proofs. I will need these numbers twice, and now you can forget everything about the origin of these numbers. What is important is that there are some rational numbers which are responsible for geometry of moduli space, and when genus G and number of marked points n are fixed, there is finite number of them, and they are parameterized by these partitions D1 plus D2, etc., plus Dn of 3G minus 3 plus n. So these numbers are useful. And one of the goals of my lecture is to convince you that they are really useful. So let me, as always, especially in combinatorics, when you have a whole bunch of numbers, it is convenient to memorize them, wrapping them into a generating function. I would not consider Witten's generating function. I would consider somehow a simpler one. This generating function would be a polynomial. To having a partition D1 plus etc. plus Dn of 3G minus 3 plus n, I will memorize this partition in the following way. I will introduce formal variables b1, etc., bn, and I will consider a monomial in these formal variables, which is b1 power 2d1, etc., times bn power 2dn. So the reason why I take this 2 is dictated by some geometric reasons. But now this monomial remembers the partition, and I can take the sum of monomials like this with coefficients which are these intersection numbers. Again, by some geometric reasons, it's convenient to normalize them slightly, not just take them as is, but to scale by some factor which depends only on g and n, which is one and the same for everybody, but also to divide them by product d1 factorial, d2 factorial, etc. We'll see in a second that it would be convenient for our purposes, but also one more reason which justifies this particular strange normalization is that this polynomial appears in several different contexts, and in particular, it provides the Weil-Petersson volume of the moduli space of bounded hyperbolic surfaces with hyperbolic boundary length b1, etc., bn. You just have to slightly normalize by this power of 2. Okay, now I prepared almost everything. Shortly, I would need to come back from polynomials to numbers and to transform polynomials into numbers, I will apply the following operator. On any monomial as we defined, it is defined as follows. So I have to take factorials of powers of my variables and multiply by values of zeta function at mi shifted by 1. And I take the product, and then I extend it to all homogeneous polynomials by linearity. Okay, now I prepared basically all sophisticated tools, and I will just take pleasure to use them. The first combinatorial problem which I suggest to discuss is the following one. We'll count metric ribbon graphs. Following Kontsevich and Norbury, we'll count metric ribbon graphs. Ribbon graph is what you see at the picture. We'll count trivalent ribbon graphs, and metric means the following. I would assume that every edge of the core of this ribbon graph has length and moreover has integer length. And then I will do the following. So here, this particular ribbon graph, it's a surface with boundary. So this is, one can check that this is the surface of genus 1 with 2 boundary components. And I will impose integer length to boundary components. And we'll count how many integer metric ribbon graphs of genus 1 with 2 boundary components of length b1 and b2 one can find. So when I impose constraints on length, it does not determine the ribbon graph, because so there are edges, and I can make some edges shorter and some edges longer, and this would compensate. And in this way, I can construct usually many metric ribbon graphs with given genus, given number of boundary components, and given length of boundary components. So the solution of this apparently naive combinatorial problem is given through polynomials which we just introduced. So if you count these metric ribbon graphs of of genus G with n boundary components of length b1, etc., bn, and as quite often it is natural to count these objects with a weight which is 1 over automorphism group of the graph, usually order of automorphism group. Usually this is just 1. So usually there are no automorphisms. Sometimes when they are, you divide by the order of this finite automorphism group. So the theorem claims that if you count metric ribbon graphs, then what you get on the right is this volume polynomial which we just introduced, plus some lower order terms. So lower order terms has actually a very precise meaning. The initial result of Kontsevich was strengthened 20 years later by Paul Norbury, who proved that the count is not asymptotic. It's actually exact count if you give right meaning to this object on the right. It's not polynomial, it's so-called quasi-polynomial. So it's a collection of polynomials which depends on parities of these variables b. For example, when something is wrong with parity, when the sum of these b's is even, then it's just 0. So for every collection of parities, you have explicit polynomial, and this also explains why I'm taking this 1 over automorphism group, because it's equality. But I need only tiny part of this result. I need only this result in the situation when all these b's are very large. And then polynomial like this shares this top degree part, and this is our volume polynomial. Okay. And now I have prepared almost everything to count my square tail surfaces. I just have to discuss combinatorial decomposition of square tail surface. So you see here in the center, you see square tail surface of genus 0, which has 1, 2, 3, 4, 5, 6, 7 conical points with angle pi, you see that at these points, we have only 2 adjacent squares. It has some other interesting points. So there are plenty of points where there are only 4 adjacent squares, but at this point, you see there are 6 adjacent squares. So the cone angle at this point is 3 pi. But I do not care about location of these interesting points for a while. I just, well, I do, but in a way which would be explained in a second. So I would like to encode combinatorics of this surface. And I will encode the following combinatorial, sort of geometrical combinatorial decomposition. I'm interested in horizontal lines. All horizontal lines are closed, and they appear in families of parallel horizontal lines of the same length. So the first family is, one of the families is here. So all this somehow part of my surface shaded in dark gray is filled with horizontal lines of the same length. So I get a flat cylinder, and I will memorize the waist curve of the cylinder, and also I will memorize the height of the cylinder. So here the waist curve has length 6, and there are two. So there is one band of squares, another band of square here. So there are 2 bands of squares. So I will memorize this height also. Then there is one more cylinder here. I take this red circle represents its waist curve. One more cylinder here, and the last cylinder is here. So my square tile surface is glued from 4 cylinders. And this is a schematic picture of my square tile surface where I forget about this kind of special points, but I memorize where are located my points with cone angle pi. So they're represented by these tiny horns. And actually, secretly, I can consider, so I already made, so here I have to make a confession that actually this is a Riemann surface and there is quadratic differential here. So I can consider corresponding associated hyperbolic metric, and I will mark all these points. And one more interpretation of a Riemann surface with marked points is so hyperbolic metric with cusps and the marked points. But this is somehow just a side remark. And I will associate to my square tile surface one more object. So it would be really kind of a plan which you get in IKEA how to construct your square tile surface. So this time I chopped my surface by all these red curves, which are waist curves of cylinders. And I decompose my surface into several components. And every component is, by construction, it's a tubular neighborhood of this blue graph, which comes from so which edges join these very special points. So you recognize that every component like this is actually a metric ribbon graph. And I associate to every such metric ribbon graph a vertex of this thing on the right. I also have, in more general situations, or here we have surface of genus 0. In more general situation, I have to memorize what are the genera of corresponding surfaces. They can be more complicated. And I also memorize the location of these special points with angle pi by these little legs. And this thing is called stable graph. And for those who somehow have intuition coming from complex geometry, this stable graph corresponds to a stable curve, which you obtain if you pinch all these short red geodesics completely. And basically, the only thing which is important for me is that there is some reasonable way to encode how we construct our surface. So vertices of this graph correspond to represent metric ribbon graphs with some limited topology. Edges represent cylinders, and for any genus G and for any fixed number n of these conical points with angle pi, there is a finite number of metric ribbon graphs, of these stable graphs, sorry, of these models. So this is basically the only thing which is important for me, because now I can suggest an algorithm how to count square tile surfaces. So we fix genus G and the number n of corners of angle pi. This data is fixed now once and forever. We'll vary it later, but now we fix it. Then we construct all possible schematic ways to get square tile surface of genus G with n corners. So we construct all possible stable graphs. It's absolutely somehow there is finite number of them, and algorithmically it's not a complicated problem. And then we'll count square tile surfaces for every stable graph individually. When we already have stable graph, we know that it has k edges. We associate to these k edges formal variables, b1, etc., bk. Actually, that's perimeters of our cylinders. And every vertex of stable graph encodes a metric ribbon graph. And we already know how to count metric ribbon graphs with boundary components b1, etc., bk. So the only thing which remains to do is to paste to these boundary components the cylinders according to our plan, and to take into consideration the fact that, well, there are twists, but the main computational part of the problem is already solved. What remains is not a big deal. We have to be careful, but basically the main part of the computation is already done. What remains is almost as easy as to count square tile tori from cylinders. And this is not a complicated problem. Now I have to say at least one word why this thing represents computation of Mazurovich volumes. So it is known that the cotangent space to the moduli space MGN is the space of pairs Riemann surface of genus G and quadratic differential on it with at most n simple poles. So as any cotangent space, we have a natural symplectic form on this total space. And thus, the symplectic form induces volume element. And of course, the volume element of the total space of cotangent bundle is infinite. But what we can do is the following. We can consider kind of bundle of unit balls. And though the base space MGN is not compact, it is known that, and this is a theorem, that the volume of this bundle of unit balls is finite. And it is knowledge of this volume is important in many equations of dynamics, because as soon as you want to perform averaging, you have to know how to normalize the entire space. And as often to compute the volume of unit ball or bundle of unit balls, instead of unit ball, you can consider balls of radius n capital and count number of integer points in such balls. And the number of integer points grows as volume of unit ball times n power dimension of the space. And that's exactly what we're doing. When we're counting square tile surfaces, we're counting integer points in these balls of radius n over ng. So I did not explain how exactly, but somehow I tried to give a hint. And believe me, this is a rigorous statement. So this is the next several slides you can consider as kind of a looking inside a black box. It's a true computation of this volume of Mazur-Rich volume for genus 2 when there are no poles. So you don't need to even try to go into details. It was just to convince you that this is not an abstract calculation, abstract nonsense. This is a very somehow computational algorithm. The pictures on the right, or what they encode what is going on the left, it's all possible ways to decompose our surface. To every decomposition, which is encoded by a graph like this, so, for example, this one. So we decompose our surface into two parts. So this part has genus 1 with one boundary component of length b2. And that's why I use as a factor my polynomial n11, which depends on one variable b2. So this part, it's genus 0 surface with, when you cut by this guy and cut and open by this guy, you get surface of genus 0 with 3 boundary components. So this cut would create 2 boundary components. This cut would create 1 boundary component. So we'll have polynomial n03, which depends on b1, b1, b2. Then I multiply by product b1, b2, which is responsible for twists of cylinders. And then I somehow recall what are the intersection numbers, and I transform this polynomial into some very concrete polynomial with rational coefficients. Then I apply my operator z, which transforms this polynomial into numbers. I sum up these numbers, and I get the volume. So I repeat, this was not to follow all the computation. It was just to convince you that you can really compute things like this. Okay. Excellent. So thank you. If you somehow, if you was distracted by your cell phone or by kids or by something, or if you just follow, if you fallen asleep, we start a new chapter and we'll start everything from scratch. Now I will tell about Mirzahani's count of simple closed geodesics. And this is extremely beautiful story, which is worth of being told anyway. So if you consider, so Mirzahani considers not flat, but hyperbolic surfaces, for example, hyperbolic surface of genus 2. And she considers not all closed geodesics, but simple closed geodesics. In general, when you have a multi-curve on the surface, a multi-curve, it's a collection of curves where smoothly embedded curves which do not have self-intersections and do not intersect between each other. So when you see something, usually we draw pictures like at the bottom of the slide. No, multi-curves look rather resemble foliations. And when you see things like this, you do not know how many connected components has this multi-curve, whether they are components which are homotopic between each other or not. So you have to work and you have to apply a non-trivial diffeomorphism to this surface, and highly non-trivial, it's not homotopic to identity, which allows you to unwrap your complicated curve into something simple-minded. And something simple-minded looks already like this curve on the left, where you might have several components which are homotopic between each other. So in this group, there are 3. So here, one which is different from all the other ones, and there are 2 here. So we have multi-curve of the type 3 gamma 1 plus gamma 2 plus 2 gamma 3. you can consider reduced multicurve, forgetting about these weights. And this is already the reduced multicurve. And what is wonderful is that the number of reduced multicurves for every genus G and every number of cusps, if they're cusps, N, is finite. For example, for surface of genus 2 without cusps, there are 6 of them, and they were presented a couple of slides before. If you are annoyed with this talk, you can go to this website, and there is this is a toy which suggests you to apply a sequence of dent twists to unwrap a curve like this to something like this. So at the beginning, it's not quite obvious, and then you somehow you learn how to do it. Now, so I started with a smooth topological story. Now let me put a hyperbolic metric on my smooth surface. In the presence of hyperbolic metric, components of my multicurve would shrink to closed geodesics. And what is wonderful, and this is not a complicated fact of hyperbolic geometry, if initial curves did not intersect and did not self-intersect, then the geodesic representatives would not intersect either. And in this way, we can, in the presence of hyperbolic metric, we can associate a natural length to any multicurve like this. Namely, we let components of this multicurve shrink to geodesic representatives. They are unique geodesic representatives for any multicurve like this. Then, since that's already geodesic representatives, we can measure their lengths. And if they were weights, we take this length with weights, and thus we associate length to any multicurve like this. And now the new counting problem is suppose we fix the topological type of the multicurve. That is, we consider this multicurve and all its brothers and sisters under their diffeomorphisms. We fix hyperbolic metric x, and we want to try to find what is the number of geodesic multicurves of this topological type of length at most L capital, which we can find for this particular hyperbolic metric x. That was the problem which solved Mirzakhani. And here's her beautiful theorem. She proved that this number, when bound for the length tends to infinity, this number has polynomial asymptotics. The degree of polynomial depends only on genus and n. It's one and the same for all topological types of multicurves. And what is particularly beautiful is the structure of this coefficient in the asymptotics. There is part of coefficient which is purely normalization factor, which depends on g and n and shared by all topological types gamma. And then the rest, there is a factor which is responsible for topology gamma, but doesn't know anything about geometry. And there is a factor which knows plenty of things about geometry, but has no idea what topological type gamma we are using. So they are somehow separated. And I'm so enthusiastic about the structure of this coefficient by the following reason. Suppose you want to consider the frequency of multicurves of one type and another, and you count, for example, separating simple closed geodesics, gamma 1, non-separating simple closed geodesics, gamma 2. You count how many you can find when L is very large. You divide one number over another, and what you get is something which asymptotically does not depend on hyperbolic metric x. So which is completely surprising, because you can, it seems surprising because you can construct very peculiar hyperbolic surfaces with bottlenecks or with plenty of symmetries and things like this. And this theorem, this corollary, says that no matter how special is your hyperbolic metric, the answer would be one and the same. So here's an example. So consider spheres with 6 cusps. A simple closed geodesic cannot bound just a disk because it would shrink to a point. It cannot go around one cusp because it would shrink and disappear in the cusp. So it has to have at least 2 cusps on each side. So it means that we have only 2 options. So either our simple closed geodesic separates our surface into 3 plus 3 cusps or into 4 plus 2 cusps. And one can count fixed hyperbolic metric, count how many simple closed geodesics of this and this type we have when the length is at most milliard, divide one number over the other, and compute the corresponding frequencies. And Mirzahani, in her paper of 2008, obtained this number for thirds. And I should say that this is not a trivial computation. So that's why I placed here confirmations by experiments performed 10 years later, because she computed everything where her theoretical prediction was absolutely correct on the nose. In a similar computation, it's very difficult not to make a single mistake in such a computation. When I am doing computation like this, I absolutely need to debug them on computer using some databases or whatever. So, and that's why I have enormous admiration for Mariam, who computed this thing and analogous things absolutely correctly. There was only one typo in her examples. Anyway, I suggest the following interpretation of this ratio. We can say that if you consider all simple closed geodesics on a sphere, hyperbolic sphere with 6 cusps of length at most milliard, then the fact that this ratio is 4/3 can be interpreted as the fact that with probability 4/7, we have our simple closed geodesics separates cusps into 3 plus 3 groups, and with probability 3/7, it separates into 2 plus 4 groups. Where the meaning of probability, it's long procedure. So you count ones and the others for some hyperbolic and only asymptotically. So basically, it's more correct term would be frequencies, but somehow probability is speaking, well, it's also an interpretation. Okay, now let me come back to my square tile surfaces. So we've seen that I can compute contributions to my Mazur-Rich volume or proportions of square tile surfaces represented by, for example, this particular multicurve. And I can also compute frequency of this particular multicurve for hyperbolic surfaces. The claim is that the corresponding frequencies, probabilities, whatever you prefer, are just identically the same. For any genus G, for any N, and for any multicurve, the frequency of multicurves as on the left, encoding square tile surfaces as on the right, are just identically the same. So from now on, so I already merged 2 computational problems. Here I was computing flat objects, here hyperbolic objects, and surprisingly, they're the same. And now I'm finally approaching the in a sense, main goal of the talk. So we've already seen the 6 possible decompositions or 6 possible types of multicurves on the surface of genus 2 without any cusps. So here's the picture. And you can compute the corresponding frequencies of these objects. Here I normalize these numbers to have total sum equal to 1. So thus I can say that if I take a complicated thing as yes, as on this picture, I wrap it to a picture like this, I forget about coefficients and I consider reduced multicurve, then that's the list of probabilities. So I get this thing with probability 16 over 63, this thing with probability 1 over 189. So we already see that non-separating simple closed geodesics are way more frequent than separating ones. And you have other probabilities. So basically, this is a complete picture, and this is wonderful. That's the final answer, and one cannot get anything better. And there is a slight trouble. And by the way, because of the previous theorem, this is also frequencies of this or that types of square tile surfaces in genus 2. Now, the trouble is that when you pass to genus 3, they are already 41 picture like this. In genus 4, they are 378, and in genus 5, they are 4,500. So 4,500 pictures and 4,500 of rational numbers. It's you have a huge atlas or maybe several volumes of it, and you have to scroll it, and then formally you have all information, but how to use it. So now the last part of the talk is what happens when genus is large, whether there are some types of pictures which basically carry most of probability and all the other ones do not show up. So it's kind of approach of a physicist. What you see in reality, some of them might be like already here, you see that these ones are very rare. And to give an example of this kind of statistical approach to composed object, let me cite two results in other domains of mathematics. So first one is description of structure of a random integer number. And as before, I define random integer in the following way. I take a random integer in a segment from 1 to n capital, uniformly distributed. And I decompose it into product of prime factors. So the prime number theorem in this language says that we get prime on the nose with approximately this probability, but we can do better. We can really decompose our number n into product of prime factors. Some of them might appear with powers. I forget about powers. I'm interested only in how many distinct prime factors are involved, and denoted by omega of n. The Erdős-Katz theorem tells that if you center this, and I consider this thing as random variable. So I center this random variable by subtracting this log n. I normalize by square root of log n. And according to Erdős-Katz theorem, the result tends to normal distribution when this n capital tends to infinity. So basically, it gives a portrait of a random integer in terms of decomposition into prime factors. Another result of the same kind is decomposition of a random permutation into product of cycles. So if you have a permutation of n elements, you can decompose it into non-intersecting cycles and can ask how often do we have 1 cycle, 2 cycles, 3 cycles, and so on. And again, theorem of Goncharov of 44 says that if you take this number of cycles, if you consider it as a random variable, if you subtract log n and normalize by square root of log n, then the result is distributed as normal. So the result is described by normal distribution, meaning in particular that a random permutation has not so many cycles. Usually it has around log n cycles. And I should say that personally, the first time I've seen a portrait of a random permutation of a combinatorial Bible of Flageolet and Sidgevik, there is a picture with several random permutations, and you have a very clear portrait of random permutations. So random permutation, it's represented by physically by circles where length of the circle is the length of the cycle. And you have several circles which are relatively long, several circles which are relatively short, and all these portraits are basically more or less the same. It's like a portrait of a human, and you would not confuse it with a picture of a zebra or something. No, they're, of course, in details they vary, but somehow you have a quite, so it's like taking off your glasses, and maybe you cannot distinguish particular features of the face or whatever, but you definitely would not confuse a random permutation with a non-random one. So, and now I want to get something like this for my square tile surfaces, or what is the same for random multicurves in large genus. For simplicity, I would assume, so this is somehow, I want to know how many cylinders I usually have, and how many these blue special layers do I have, and what are usually the heights of the cylinders, what are the length of these red curves, just all this information. So please give me a portrait of a random square tile surface, or what is the same of random multicurve. And actually it is possible to do. And several features of this portrait are like this. First, so you should hate me for this picture because I'm working with hyperbolic surfaces and I am killing all geometry. The hyperbolic surfaces, it's wrapped like this, and it's very somehow has many ties. It's like polymer molecule, and what I do, I unwrap it completely and I make a sausage. And please do not, don't think that this is hyperbolic picture. It would give completely wrong intuition. Hyperbolic surfaces of large genus are all but sausages. This is a topological picture. And topologically, what I would like to say is that when you have a topological picture of a multicurve, you chop your surface by all components of your multicurve, and you still have a connected surface. So a typical multicurve does not disconnect the surface. In language of square tile surfaces, it's even more striking. In the language of square tile surfaces, this result means that I assume that there are no cone angles pi, but there are more complicated cone angles, and there are plenty of them. And all of them, if you take a random square tile surface of large genus, all these conical singularities live at the same horizontal level and at the same vertical level. It is exactly the opposite of, I don't know, of intuition, which comes from Morse theory, where all singular points of the function live at different levels. No, here they absolutely want to sit at the same level horizontally and at the same level vertically. And so there is, if you consider the corresponding ribbon graph, it's just one component ribbon graph, and there are cylinders which go out this and come back to this ribbon graph, and the number of cylinders, it's roughly log g over 2. And if you take from this to this part of log g, then you see basically all square tile surfaces or all multicurves. So experimentally, I never worked with surfaces of genus more than, I think, 20,000. And for 20,000, if you take log g and even half of log g, so basically it means that you have, I don't know, 6, 7, or 8 cylinders or something like this, and not 3g minus 3 potential ones. No, you never see surfaces with this number of cylinders. And also, another part of the theorem says that actually cylinders are usually not very tall. If you consider conditional probability, if you consider only square tile surfaces tiled having at most, I don't know, 50 cylinders, then with probability which tends to 1 when genus tends to infinity, all of them would be constructed from a single band of squares. If you consider not a conditional probability, but if you consider all at once, then approximately 71%, so square root of 2 over 2, would have all the cylinders constructed from a single band of squares. But there would be other ones with somehow 2 bands of squares. If you impose bound at most m bands, then you replace your square root of 2 by this thing. But still, however, the mean value of the number of bands of squares all these probability distributions and so on, it's comparison with random permutations, except that they are random with respect to some biased measure, and you can compute everything actually. But I would like to speak about something different because I have not so much time left. All these results were possible to several breakthrough results of Amol Agarwal. So he proved our conjecture on asymptotic count of all square tile surfaces, otherwise nothing would be possible. And here's the asymptotics. I should say that analogous statement for not all square tile surfaces, but the ones where you specify how many conical points you want to have with angle 3 pi, separately 4 pi, separately 5 pi, and so on. So if you impose more constraints on your square tile surfaces, then the corresponding square tile surfaces represent certain natural strata in the moduli space of quadratic differentials. And conjectural formula is very similar, but now for the moment, we don't know how to prove it. And now I would like to come back to my scary object. So please take a breath. It's almost over. That's the true recurrent relations which enable to compute all Witten-Kontsevich correlators. You have to know these first two basic ones. This corresponds to, so this is genus 0, 3 mark points. The corresponding moduli space is just 1 point. And it's almost by convention we assume that the corresponding integral is 1. This is more interesting. This is genus 1 with 1 mark point, so it's moduli space of tori with 1 point. One can compute this number, it's 1 over 24. And starting from these two, you can compute everybody in the following way. So there is string equation which allows you to get rid of this element 0 in your partition. So you see you have the 0 on the left, and on the right, the partition is already simpler and there is no 0. There is so-called dilaton equation, which allows you to get rid of entries 1. So here we have this entry 1 and some partition d1, etc., dn. And here we just erase this 1 from partition. We consider corresponding correlator and we get this coefficient. And now there is this scary Virasoro constraints. So when you have partition like this, I somehow distinguish the first entry and I represent it as k plus 1. And we express this guy as linear combination of the following correlators. So this correlator, it has shorter partition. So we change this k plus 1 to k, and we add this k in turn to the first entry, to the second entry, and so on. So this is a very sympathetic term because our partition gets shorter and simpler. The second term, well, it is in some sense simpler because it's genus G minus 1, but unfortunately it's longer. So we split our k minus 1 into the sum R plus S, and instead of 1 entry in the partition, we get these 2. And the third term seems completely scary because we decompose our partition into 2, and there is this all kind of products of correlators. But somehow it was known to experts that the last term dries up in that genus. It does not contribute much. You have to prove it formally, and Agarwal proved it. And as soon as you prove it, your recursion pretends to be like this. There is a term where partition shortens and another term where partitions gets longer. And this is nice because when we get partition of one element, we know the answer, and this is somehow nasty. And Agarwal noticed that morally, with probability, so not with probability, this thing carries sort of 2/3 of the answer, and this thing carries 1/3 of the answer. And he modeled this completely deterministic recursion as a random process where with probability 2/3 you get shorter object, and with probability 1/3 you get longer one, and 2/3 are considerably larger. So with high probability, very fast you get it. And this probabilistic approach to this purely deterministic recurrence relations allowed to prove the following uniform asymptotic formula for all these correlators. So when genus is large and the number n is not too large, so n should be smaller than square root of g, then you can replace all these correlators by just product of factorials with arrow term, which is uniformly small for all possible partitions. So this is like Stirling formula for correlators in a sense. And this approximation allows to work with these contributions of square tile surfaces to volumes and so on. And basically, this was the key instrument for all our computations. This is one more slide to show off. So Serежа mentioned Arnold, and the name of Arnold was also so name of Arnold was mentioned twice. Surprisingly, this technique allows to advance and partly solve his problem formulated more than 20 years ago. And part of this problem can be reformulated like this. Suppose you have kind of a braid on the surface of genus G with two boundary components. So you consider random braid, and you consider random gluing of the ends to get closed curves. The question is, what is the probability that we'll get a single connected component after the gluing? The answer to this problem, and I don't think that Arnold could foresee it, is expressed in terms of this Maser-Rich volume. So that's the answer, except that it's Maser-Rich volume, not of quadratic differentials, but of holomorphic one forms. They are known. So that's the asymptotics. That's the values for. So in genus for one, it's easy to compute. It's just so instead of the surface you have cylinder. But for other ones, you already have to mime. I don't know how to talk. So at the very center of Paris, there is a street which is called the Street of Little Squares, and you see the square tiling. So it's a pleasure to work with square tile surfaces in Paris. Thank you very much for your attention.
Thank you very much. Now it's time for questions. You can unmute yourself and ask questions directly.
Anton, on one of your transparencies, you have a ransom curves. I guess it was random curves, but you better avoid ambiguities.
I would be absolutely unable to find the slide right now. If I would know, I would correct before. Thank you.
Or you can claim some ransom. It's also a solution.
Yeah, you should pay for that.
Anton, I have the following question. So on one of your first slides, you had this interesting function Z from polynomials to numbers.
Yes.
It's some zeta function which you
Yes,
get.
this one.
What
Yes.
is its role in your story?
So it appears as follows. So I have to come to this, yes, to this algorithm. So for each stable graph, so we count our square tile surfaces like this. So we have some graph. It encodes how our surface is decomposed into ribbon graphs. And ribbon graphs, they have already these horizontal parameters B1, etc., BK, which represent the waist curves of our cylinders. And then to construct the entire surface, we have to paste in these cylinders and to compute the result. And the counting goes like this. The cylinder can have length, the height 1, or it can have height 2, but etc. And you have to perform summation with respect to these heights. And this summation with respect to height gives series of the type 1 plus 1 over 2 squared plus 1 over 3 squared. And sometimes it's squared, and sometimes it's power 4, and sometimes it's power 6. So basically, from this summation, you get these zeta functions. And by geometric origin of the problem, you get only zeta values at even integers, which means that you have powers of pi with rational coefficients, fortunately. So that's the origin of zeta functions, and they are already present in the works of Mirzahani. And extremely challenging question, for me, challenging question. In a similar count of square tile surfaces which correspond to abelian differentials, appear multiple zeta values conjecturally. So one of the conjectures is that contribution of K-cylinder square tile surfaces to Maser-Ricci volume of abelian differentials is a rational linear combination of multiple zeta values. I'm extremely challenged by this conjecture, so I would like to prove it. And also, if it's really true, to my mind, it's some indication that this contribution of K-cylinder square tile surfaces, which sounds somehow bizarre. It's from geometric point of view, it's quite artificial thing. So if it's really combination of multiple zeta values, to my mind, this indication that there is a geometry beyond, because I do not believe in coincidence, and usually multiple zeta values are responsible for periods and for some beautiful algebraic geometry.
Thank you very much.
But here it is easy, fortunately.
More questions? Anton, may I ask about the number P1 at the very end? It's Arnold's problem. Yeah. So it's 6 over pi squared. Of course, pi squared over 6 is a familiar number.
Yes. Yes.
Any relation?
Of course. This is an exercise, and an exercise is like this. Take a cylinder with several lines which go from one boundary to the other. So take a random cylinder like this. So random perimeter and random gluing. The question is how often your collection of strands would create a single connected line. So basically it's equation about the frequency of coprime numbers between pairs of integers. And coprime numbers, so the density of coprime integers among pairs of integers among all pairs of integers is 1 over zeta of 2, this 6 over pi squared.
Okay, thanks. Yeah.
So this number is easy. So it's the only one which, to my mind, is easy to compute at this picture. But starting from already for this surface, it is non-trivial. And I don't know any other way to compute it except going through count of square tile surfaces and Maser-Ricci volumes and such.
Okay.
Yeah,
thanks.
so I agree that the problem seems extremely naive. Yes.
More questions? Well, if there are no more questions, let's thank the speaker again. Thank you.
Thank you for your attention, and I'm happy to present this somehow, these several areas of mathematics and in particular results of Maria Mirzahani, which I find extremely beautiful, and results of Amol Agarwal, and so there. Thanks for your attention.
Thank you very much, Anton. Fantastic
Thank you very much.
Fascinating. Yeah.
Okay, so and
Thank you. Thank you.
And the recording will be available after it's edited a little bit.
Great.
Thank you all.